Hello students, welcome to lesson 2 of module 1, reaction stoichiometry. I am still your facilitator, Engineer Elizabeth Espiritu. So let's take a look at what we are supposed to study under this topic. At the end of the lesson, you should be able to understand and calculate problems relating to chemical equations, balancing chemical equations, calculations based on chemical equations, the limiting reactant concept, yield of reaction, gas stoichiometry, and solution stoichiometry. So for the first part of our lesson, and this is step 1, I would be discussing with you the first three in our objective. So here goes the lesson. So what is a chemical equation? It is a symbolic representation of a chemical reaction that shows reactants on the left side of the equation and the products are on the right side. So relative amounts of each are represented by using stoichiometric coefficient, which balances the equation. So reactants forming products, there is an arrow at the center, meaning to say the reactants yield products. For example, this equation represents the reaction between lithium and water forming lithium hydroxide and hydrogen. So any equation can be interpreted as referring to the nanoscale or macroscale. Remember nanoscale, that is in terms of atoms and molecules, while macroscale is in terms of the number of moles of the different reactants and products. So this equation is balanced. So it can represent two formula units of lithium and two molecules of water, a covalent compound, forming two formula units of lithium hydroxide and one molecule of hydrogen gas. So this may refer to these small nanoparticles like this of matter. Now it can be in another proportion, in another number, but in direct proportion with what is actually represented in the balanced equation. So this equation represents a reaction involving four formula units of lithium and four formula units of four molecules of water, four formula units of lithium hydroxide, and two molecules of hydrogen gas. Take note that we made use of different representations for an element being represented by the formula and an ionic compound being represented by formula units, whereas these are covalent particles, water and hydrogen gas, so they are called molecules. On the macro scale, that is in terms of the number of moles, the coefficients of the balanced equation represents number of moles of the reactants and the products. So 2 moles of lithium, 2 moles of water, 2 moles of lithium hydroxide, and 1 mole of hydrogen. It can be in terms of Avogadro's number as well, no? But let us limit the use of the balanced equation for our particular lesson under this topic, and that would be the use of it in terms of the number of moles. So this gives us the mole ratio between any two. The balanced equation, the coefficient of the balanced equation gives us the mole ratio between any two of the reactants and products involved in the chemical reaction. When we represent a chemical reaction in terms of a balanced chemical equation, we abide by a law of nature known as the law of conservation of mass. So according to this law, mass is neither created nor destroyed in any chemical reaction. As such, the number of atoms of each element must be the same on both sides of the equation. For example, Sodium bicarbonate with hydrochloric acid reacts to form carbon dioxide, water, and sodium chloride. So whatever number of sodium, hydrogen, carbon, and oxygen and chlorine present in the reactants, there should be the same number of the same elements in the products. So in this example here, without writing any coefficient, the equation is balanced because the number of sodium atoms in the reactant is the same as those in the products, as well as all the other elements present in the reactants have the same number in the products as well. So there is a need to balance some chemical equations because not all chemical equations are just like in the previous example. So for most chemical equations, we need to balance them. So what are the rules in balancing chemical equations? So we are going to deal with simple chemical equations only. So we balance the equation by a method called inspection, the method of inspection. So what is inspection? To inspect and we count the number of atoms in the reactants as well as in the product. So step number 1, write an unbalanced equation with the correct formula for all the substance. So writing the correct formula is the key. If you write it wrongly, then there is no way for you to be able to balance it correctly. So next is to balance the atoms of one of the elements. And when we do this, we always start with the most complex molecule. We look at the most complex molecule in the equation, the most complex formula in the equation, and then we start our consideration by picking up one particular element in that complex formula. So change the stoichiometric coefficient depending on the need. So we have to make the number of each element in the reactant the same as in the product. Do not alter the chemical formulas. If you are confident that you have written it correctly, there is no need for you to change that. So when we balance chemical equations, we do not change the subscripts. We only change the coefficient. That is the number we write before the formula. So you start with one, followed by another, and then balance the remaining elements. So it is easier said, or it is easier listed here than done. So let's try to work on some equations. Let's balance some chemical equations now. Okay, so let's start balancing equations from this example here. So balance the equation representing the reaction between aluminum and ferric oxide, forming aluminum oxide and iron. So step 1, let us consider the number of atoms of each element in the equation on both sides of the equation. So 1 aluminum, 2 iron, 3 oxygen, 2 aluminum in the product, 3 ang oxygen, and there's only 1 iron. So obviously you can identify the substances who do not have the same number of atoms in the reactant as well as in the product. So iron is not balanced and aluminum is not balanced, while oxygen has the same number of atoms on both sides of the equation. So let's balance iron first. So we pick up ferric oxide as our complex formula. If there are 2 iron in ferric oxide here in the reactant, then we place the coefficient 2 for iron in the product. So we are done with iron, okay? So next, let's take a look at the other unbalanced element, and that is aluminum. So if there are 2 aluminum in the product, then we can write safely the coefficient 2 for aluminum in the reactant. So this normally balances out our equation. So if we count the number of aluminum and iron and oxygen atoms in the equation, the equation is now balanced. Now let's go to the next example. Here is another example that looks quite complicated because some chemical formulas contain so many different atoms, and oxygen in the reactant appears in two different products. So it may be quite complicated to balance as it looks, but if we take careful considerations, we can easily do that. So let us first analyze and try to determine which elements are not the same on both sides of the equation and which are not. So carbon is not balanced, hydrogen is not. Seems like all of them are not balanced. No? All of them are not balanced. So let's consider rule number 1, pick up the most complex formula in the equation and start from there. So this is the most complex, and I would be looking for the partner element on the other side. So if there are 2 carbon in this most complex formula, I will look for the corresponding carbon atom on the other side. Okay. So one rule that was not mentioned in the rule is that when you are comparing elements, start with elements that appear only once in the product. So if oxygen appears once, suppose you were able to pick up this as your most complex formula, N2O4. And then you start off with oxygen. Oxygen appears only once in the reactant, but look, it appears twice in the product. It will make your balancing of equation so complicated. So do away with elements that appear in so many substances last. So always start with elements that appear only once in the reactant as well as in the product. So I'm starting off with carbon, 2 here, and carbon appears in carbon dioxide and there's only 1. So I can make the number of carbon atoms equal or the same by placing the coefficient 2 before carbon dioxide there. And then hydrogen next. Hydrogen, 8 here. Hydrogen appears only once in the product. It is in water and there are 2. So if I want to make it equal to 4, then I will be multiplying, or I would be placing the coefficient 4 before H2O. So that makes the hydrogen balanced. Now, I would want to go into nitrogen. So nitrogen appears in the rocket fuel as well as in dinitrogen tetroxide. Okay, so there are 2 in the first reactant and there are 2 in the second reactant, total of 4, while in the product it appears only once and there are 2 of them. So if I place the coefficient 2 before nitrogen, then I would be making the number of nitrogen atoms the same as those in the reactant. And then oxygen next, 4 in the reactant, and there are 4 plus 4. 4 from water, 4 from carbon dioxide, so that's a total of 8 oxygen atoms. Oxygen is here, so to make the number of oxygen atoms the same as those of the products, then I should be placing nitrogen here, 2 here before N2O4. And then I would be adjusting my nitrogen because my nitrogen would then be a total of 2 plus 4 equals 6. So I should be adding a coefficient here to make the number of nitrogen atoms equal to 6. And that would be a 3. So here is our balance equation. Okay? So patience is what you need when you balance equation. You don't need science, mathematics, rocket mathematics to be able to accomplish this. So what if there are polyatomic ions? So let's say we have a reaction between ionic compounds, and you know the formulas of some ionic compounds containing polyatomic ions uh, might be terrible, no? So if polyatomic ions are present in the chemical reaction and you notice that they appear as the same polyatomic ions on both sides of the equation, then you consider these polyatomic ions as single units. So do not separate them into their constituent elements anymore. You do that at the last just to finally check if the number of atoms are the same on both sides of the equation. But if you see the same polyatomic ion, like let's say the nitrate, appearing as the nitrate in the product, then you count them as one whole nitrate ion, one whole sulfate ion. So this is the reaction between sodium nitrate and sulfuric acid, forming sodium sulfate and nitric acid. So obviously sodium does not balance the nitrate ions. They are the same, one here and another one there. Hydrogen, there are two in the reactant. In the product, there's only one there. And the sulfate ion is counted as one whole SO4. So there's only one. So which of these does not balance? Sodium. So there are two of the sodium. We place the coefficient 2 before sodium nitrate. Okay, so we balance sodium nitrate. We balance sodium by placing the coefficient 2 before the formula of sodium nitrate. Okay, so alin pa, which one is the problematic one? Hydrogen. So the sulfate and the nitrate, we do not have problems. Hydrogen. 2 here, there's only 1 here. So we place the coefficient 2 before HNO3. So let's see if the equation is not now balanced. It would make the number of nitrogen atoms, the nitrate ions, equal to 2 if we place the coefficient 2 here. Well, when we place the coefficient 2 before sodium nitrate, it made the number of NO3 ions equal to 2, just the same, no? So, counting the number of particles present as well as the elements that are present on both sides of the equation, now we have a balanced chemical equation. Hello students, welcome to lesson 2 of module 1, reaction stoichiometry. I am still your facilitator, Engineer Elizabeth Espiritu. So where do we make use of those balanced equations? We make use of those balanced equations to do calculations based on chemical reactions. So chemical equations represent chemical reactions. So if we are to follow or abide by the law of conservation of mass, which is the law of nature, equations to be used in the calculations should be balanced. So the first step in solving reaction stoichiometry problems is to write balanced chemical equation. Second step, if the mass is given or all other quantities are given of a particular substance, then that quantity must be converted into its corresponding number of moles. For example, if the mass of a substance is given, let's say A is a reactant in a chemical reaction. If its mass is given, then we convert that given mass into the number of moles corresponding to substance A by using the molar mass. And we did that under composition stoichiometry, right? Okay? And then we refer to the coefficient of the balanced equation to calculate the number of moles of the partner substance that are being asked for in the problem. So we work on two substances at a time in a particular chemical reaction. We relate two different substances at a time. So we make use of the coefficient of the mole of the balanced equation. It serves as the mole ratio between substances A and B. So A has the given quantity, B is the substance in the reaction whose quantity we are being asked to find. So using the mole ratio, we convert the number of moles of A into the corresponding number of moles of B. If the mass of B is being asked for, we simply multiply the number of moles of B with the molar mass of compound B. So this is the whole picture. This is the whole picture. Meaning to say, we can remove some parts of this picture if they are not needed. For example, if what is given is just the number of moles of A and you are asked to determine the number of moles of B, then we just make use of this part of our solution. No? So if given is the number of moles of A and you are asked to determine the number of moles of B, then your solution would just be this part. Okay? On the other hand, if you are given the mass of A and you are asked to determine the number of moles of B, then your solution would just be include this part. So you will just be using the molar mass of A to convert it into its number of moles and use the mole ratio to find the number of moles of the other substance. Sometimes you are given the number of moles of A and you are asked to determine the mass of B. So that means to say you are to So to continue with the discussion from the previous slide, if for example you are given the mass of A and you are just asked to determine the number of moles of B, then you do away with the last step. You don't have to make use of the molar mass of B because you are just asked to determine its number of moles. Now let's work on some examples here so you can better understand what I was talking about in the previous slide. So, for example, you are asked to determine the mass of carbon monoxide that is required to react with 146 grams of iron 3 oxide. So, step 1, as I said, is you always begin with a balanced equation. So, carbon monoxide and iron 3 oxide, when balanced, would be something like this. So, it is always advisable if you can write the given quantity beneath the chemical formula. In most of the problems here, I did that. So you are given a quantity of the reactant ferric oxide and you are asked to determine the mass of the partner carbon monoxide in the reaction. So we start with 146 grams of ferric oxide. We convert it into the corresponding number of moles by dividing it with the molar mass of ferric oxide. As I said, in some problems, the molar masses may be given to you but in most problems, they're not. So you have to calculate molar masses. Okay? And then the next thing is add the mole ratio. We use the mole ratio. So we have found the number of moles of Fe2O3. When we use the mole ratio, we determine the number of moles of the substance that is in question. Now, since it is the mass of carbon monoxide that is asked for, then the next step is we would be multiplying this with the molar mass of carbon monoxide. So as in the previous slide, I told you that if you are asked to determine the number of moles of carbon monoxide, just the number of moles of carbon monoxide, then you would be stopping your solution here. But this problem asks for the mass, so let's proceed with the last step, and that is using the molar mass of carbon monoxide to determine the mass of the product corresponding to 146 grams of ferric oxide. So this is the entire solution for this problem here. So cancellation of units is necessary for you not to be confused because of the so many units. So if you do not want to place units, it's up to you. As long as you are sure and confident that you have placed the numbers where they are supposed to be placed. So we cancel units just to make sure that we did the presentation properly, and then the numbers would be arithmetically operated using your calculators. So let's have another example. Still on the same chemical equation, what mass of carbon dioxide can be produced by the reaction of 0.54 mole of iron oxide with excess carbon monoxide? Same reaction, same chemical equation is going to be used here, but this time what is given is the number of moles of the reactant iron oxide, and you are asked to determine the mass of carbon dioxide. So we do not have to convert anymore because the number of moles is already given. So we start with the number of moles of ferric oxide, and the first factor that we are going to make use of is the mole ratio, so that we can easily transit into the next substance, carbon dioxide, from ferric oxide. So we have shifted from ferric oxide to carbon dioxide using the mole ratio. Take note that since carbon dioxide is in question, it is at the numerator and ferric oxide is at the denominator. Mass of carbon dioxide is being asked for, so the next conversion factor would be the molar mass of carbon dioxide. So this is the entire picture of that solution to that example. And then we do the cancellation of units to avoid confusing ourselves with the so many units that are there, and that to make sure that we have placed the factors properly. We have used the conversion factors properly. So this is the end of part 1 of our lesson. So let's now proceed to part 2. Thank you very much for watching. Let's go next.